Hello students. So today we are going to discuss about the applications of Newton's laws in non-accelerated or you can say non-inertial frame, which are accelerated frame of reference. Okay. So let's go into this detail. So first of all, reference frame or frame of reference can be classified into two categories, right? One is inertial frame, and another is non-inertial frame. What are inertial frame? Inertial frame are those frame which has zero acceleration. Okay, and non-inertial frame means there is some acceleration. Acceleration is not zero. Okay, so now let's understand. And Newton's laws of motion are valid in inertial frame of reference. If it's a non-inertial frame, we have to convert it into inertial frame by applying the concept of pseudo forces. Okay, so we can note that Newton's laws of motion are valid for inertial frame. Okay, non-inertial frame or studying an object, the dynamics of an object in non-inertial frame can be studied by applying the concept of pseudo force. So in non-inertial frame, the concept of pseudo force can be applied to use Newton's laws. Okay, what is pseudo force? How can we apply that we are going to study? Okay, let us go through it. So let's understand the example by lift. There is a lift, let us say, and in this lift there is, let's say, there is a block, there is a body in this lift. Okay, this body or this block in this lift, we are going to study this body, and the lift is under acceleration. Okay, lift is going upward. So there are two observers. One observer is in the lift and another observer is on the ground. Okay, this observer is on the ground. So this observer is observing, and this frame is inertial frame, right? This person in the lift is non-inertial frame, right? So let us study the forces on this body from both frame of reference. Okay, so first we are going to study the forces acting on this with respect to ground. Okay, let's draw free body diagram. So with respect to ground, if you see, this person is seeing that it is going up. So for this person, this object, right, should also have the same acceleration, isn't it? If you draw free body diagram, let us draw free body diagram. So what are the forces acting? You will see that there is mg acting downward, and there will be normal which will be acting upward. And because this is under upward acceleration, so normal must be greater. So he will write normal minus mg, Newton's second law is applying, is mass into acceleration. So according to him, normal must be mg plus a. Right? Now let us understand the free body diagram from the viewpoint of the non-inertial frame. Okay, so this is the object. Now from this non-inertial frame, again draw free body diagram. So mg acting downward, normal acting upward. But you need to note that the observer does not find this to be accelerated because observer is also under acceleration, right? So observer is in the lift, he is also under the same acceleration of the block, so he does not find the object to be moving. So according to that observer in the lift, this object is at rest. Okay, this object is at rest. Then what he will think? He will think that this normal is equal to mg. He will try to just balance it, and then we see that the contradiction happening here. This normal, which is mg plus a, here it is just mg. How is it possible? Right? Because normal is a real force. Normal contact force is a real force. And it cannot be different values. It must be unique, right? Because it is due to the interaction between the block and this floor of the lift, right? So it cannot have two different values. Where is the contradiction here? How can we then understand? Because here the observer is under acceleration. He is trying to he doesn't see this object to be moving, right? So in this case we must apply in non-inertial frame. There must be some concept of imaginary force that we have to understand. So what happens is that we need to apply a pseudo force in downward direction, which is m into a, and then we can balance it. So this is not correct. So we are going to apply now this force m into a. This is the pseudo force. Now when you try to balance it, so normal will balance ma plus mg. Now normal will become same as mg plus a, right? So here we have to apply a pseudo force in order to make the object balance. Why we apply it? Because it is under acceleration. So in a non-inertial frame we must apply a pseudo force in opposite direction of the acceleration of the frame itself. The lift is going up, we have to apply force m into a in downward direction. Okay, so pseudo force is an imaginary force which has to be applied in the free body diagram, and it is applied opposite of the acceleration of the frame, and this value will be mass into acceleration. This is what we should know. That's the concept of pseudo force. Now in lift going up, this mass become mg plus a. Now this term g plus a can be also written as g effective, right? So this g effective we can write as g plus. So the Earth's acceleration due to gravity seems to increase as if the person has entered into a different world altogether. The gravity seems to be changing for the person who is in an accelerated frame of reference. Okay, so this is the g effective that we take when the lift is going up. Similarly, if the lift is going down, the g effective can become g minus a, right? So if the lift is going up with acceleration a, then we take like this. If lift is going down, then acceleration direction has changed, so g effective will become g minus a. And what will happen if it is free fall? So free fall means a becomes equal to g. This is free fall, right? So then g effective becomes what? G minus g becomes equal to 0. So in this case the normal will become 0. So this is called apparent weightlessness. Okay, this is apparent weightlessness, right? So these are certain concepts which we can apply in the problems. Now let's see how g effective concept can be applied. Suppose if you take, for example, a lift which is going up, and inside this lift a object is hanging from a string. Okay, so this is the object or the block which is hanging. What is the tension? Let's say it is going up. Now here the observer is, let us say, and with respect to this, if you want to draw free body diagram, so tension is upward, mg is going to act downward, and pseudo force you must apply downward, right? M into A. This is the pseudo force. So you can see that tension will balance with respect to him, it is balanced. So this is again mg plus A, which is nothing but G effective. Okay, so tension will balance with this mg effect. Okay, same manner if it is going down, it will become mg minus A. All those concepts we can apply here. Okay, similarly if a person is standing, the same way normal is the apparent weight, and we can find the apparent weight and all that, right? Okay, now let us understand this concept. There is a question where you can understand how to apply the wedge constraint. Suppose this is a body wedge and this is a smooth surface, and on top of this a block is kept, right? This block has mass small m and this mass capital M. Angle is theta. All the surfaces are smooth. This is also smooth. Okay, and this is released. It is released. Now it is given that the constant motion concept will come, right? So there is a constant here. The wedge can only move in this direction, horizontal. So as this is going down, this will go this direction, right? This is acceleration of the wedge, right? You can write this as acceleration. Let us say acceleration 1. Okay, and with respect to this, it will go this direction. So this is the acceleration. This is second. So acceleration 2 with respect to 1, right? This is what it is. Now here the question is how to draw the vectors. So we have discussed that. Forces, if you want to see, let's see the forces first. So on this block, the forces that are going to act is mg, small mg. Now with respect to, let's say observer is on this wedge, then pseudo force you need to apply in opposite direction. So there must be a pseudo force as ma1 in this direction, right? Now other forces are normal, right? So these are the three forces which are going to act. And now let us resolve the forces. Which direction we are resolving? We are going to see relative forces, so that means along this direction and the perpendicular direction, right? So this angle is theta, so obviously normal and this will make the same angle theta here also, right? So this angle is also going to be theta. Now we need to resolve the forces. So we need to resolve along the plane and perpendicular to plane. So mg, this direction, mg cos theta, this direction, mg sin theta, this direction, ma1 cos theta, this direction, ma1 sin theta. So now relative, this free body diagram is from a non-inertial frame. Okay, this is FBD from non-inertial frame, non-inertial frame. So where is the pseudo force? This ma1, this is the pseudo force. Okay, this is the pseudo force. Now here it will be balanced in this direction, right? Normal and ma1 sin theta, let's balance it. So normal plus ma1 sin theta will balance mg cos theta, right? Similarly in this direction there is a net force. So net force is equal to mg sin theta plus ma1 cos theta, right? This net force is equal to mass into acceleration, but this acceleration is acceleration to 1. Okay, so from here you can calculate acceleration to 1. Acceleration to 1 will be g sin theta plus a1 cos theta, right? Okay, and normal also we can calculate. Normal can also be, so let's write this as equation number 1. Let us write this is equation number 1. From here normal can be calculated. This is equation number 2. Equation number 2. Okay, now if you see the free body diagram of the wedge, let us see the wedge free body diagram. So if you see the wedge, the forces acting, because horizontal is, it is going to move, so horizontal only forces you see. So this normal which is acting here, from bottom there will be also its weight capital mg and some normal from ground, let's say n1. This normal is the common normal. This normal we should try to resolve, right? So this normal is making same angle theta with the vertical, so this direction will be normal cos theta, sorry, that will be sin theta, normal sin theta, and this direction will be normal cos theta. So horizontal force normal sin theta is the net force acting towards, right, this direction. So this is the acceleration, which is acceleration a1, right? So this normal sin theta is capital mass into a1, right? So this is also the third equation. So we have lot of equations here, you can see. So we have equations of 1, 2, 3. We can substitute normal here, and definitely we can calculate a1, right? Can we calculate a1? Use equation 1 and 3 and calculate acceleration a1. So using equation 1 and 3, what do we get? From this normal we can substitute there, right? If you substitute normal there, what will happen? It will become m a1 by sin theta plus small m a1 sin theta is equal to mg cos theta. So from here I think we can calculate small a1, right? Small a1 you can take out, and then it will become what? This will become mg sin theta cos theta divided by capital M plus small m sin square theta. Now see, this is a very important result. If you know these formulas now, then within few seconds you will solve question. This is how you can compete, right? Okay, once you know a1, you can calculate this normal also if you want. The normal which is acting, substitute here m a1 m by sin theta into a1. A1 is this, right? So multiply small m g sin theta cos theta. I think sin theta factor will go away, right? By m plus m sin square theta. So this sin theta factor will go away. So normal can be calculated now. Capital M small m g cos theta divided by capital M plus small m sin square theta. Okay, so this is what is the normal. Normal can be now calculated like this. We can calculate normal. Okay. Then what about A2? A21. Now we know A21. A1 we know, we can substitute in equation number 2. Let us substitute that. So let us try to calculate A21. A21. What will be A21? A21 is g sin theta plus A1 cos theta. G sin theta plus A1 cos theta. So A1 cos theta will become small mg sin theta cos square theta, right, by m plus m sin square theta. So from here A21 will become, the sin theta will come out, right? So denominator of course will be same, m plus m sin square theta. But in the numerator we have, let us say, g sin theta comma. So this will be 1 plus capital M plus small m sin square theta. Sin square cos square will become 1. Correct. So g sin theta will come out, right? G sin theta will definitely come out, and here we will have capital M, right? Capital M will be there and small m will be there, right? Isn't it? Capital M and small m. Yes, this is what is the acceleration e21. Now we know this acceleration e21. So you can see, you can calculate all the things. Now sometimes they will ask that this acceleration of a2, they will ask you to calculate a2. Remember I told in one of the video how to calculate a2, acceleration of this block. So now how to calculate a2? So if you see here, this is the inclined plane, right? So this is the acceleration of a21. Acceleration of this a1 is this. Now you need to add the resultant of this, right? The resultant of this need to be added, and that will be the acceleration of a2. This will be the acceleration of a2, right? So suppose sometime they can ask what is this going to make angle with the horizontal or vertical line, or sometimes they will ask. Okay, so this is the horizontal line, isn't it? This line is the horizontal line. So how much angle it will make? Let us say this angle is some angle, you can assume, right? Let's say this angle is making angle beta. Okay, so how much this angle will be? So you can calculate tan beta. I told, so tan beta can be calculated, and let's say this is angle alpha. They can ask anything. So if you calculate tan beta, remember the formula for tan beta: p sin theta. B means other one, a21 sine sine of total angle, right? That is alpha plus beta. Alpha plus beta sine of this by b sin theta by a plus b cos theta, a plus b cos theta. So if you simplify this, I am not going to simplify further. I think you have to substitute a1 and a21 here. Substitute it. What you are going to get here? Okay, what you are going to get here is very surprising result. What is the surprising result? When you solve it, you will get I will just write here the result finally. 1 plus small m by capital M into tan theta you will get. Okay, this result better you remember it. Okay, so it will make this angle with the horizontal. Okay, so this we can remember. Some of this, now this slide which I have shown here, almost all the important concept is covered in this, constraint motion and pseudo forces. Very important, concept for JEE main as well as advanced, right? These results may go further detail in advanced, but for main this is too much anyway. But this formula will be very useful if you remember. Okay, right? But concept is important. If you understand, then you can solve any concept related question. Okay, then we are going to see the constraint equations in springs. In springs, that's also important topic. In springs, how constraint relation can be applied. Okay, so let us take some examples to understand it. And generally the questions they will give for calculating of equivalent spring constant. Okay, so constraint equations in springs. The problem in spring is that the length of springs will change, right? Springs length will not remain constant. So let's take example. These will be some case studies you can see. So take case 1. Suppose there is a like this, and there is a spring like this. This spring is passing through a pulley. This is a pulley, right? And then it is passing through another pulley, and this is fixed here, and then it is connected like this with some other on this. Okay, let's say the spring constant of this is k1 and this is k2. Okay, and here a block is suspended, some mass is there, let's say smaller. Now they are asking that we want to reduce this system into equivalent system. Equivalent means there will be just one spring and the same block is connected with that system. Okay, that's called equivalent system. What is the k equivalent of this system, they are asking. We need to find k equivalent, right? So how to solve this step by step, that is what first we have to know. Okay, here the length of this spring will change, so we have to apply properly, right? So let us say you are applying, so first draw free body diagram here. Here the forces is mg, here there is a tension T, the same tension is also acting downward on this pulley, right? And here pulley has no mass, you know, so no mg will be there. Here tension will be there, here also tension will be there. It is balanced, so this tension will be T by 2, T by 2. Tension in the same, you know, spring will be same, so here also tension will be T by 2, right? Same tensions will be acting like this. This is how we can show tension. Okay, now this tension is equal to mg, right? This tension is equal to mg because this right now this is balanced, so we consider in equilibrium this tension is equal to mg. Now this side, first of all, what is the relationship between the displacements and other things? By constant equation we can study. So let's say that this is the pulley. This pulley you can name as P because it is moving. So from a fixed point, again fixed point means you can consider this. This will be the XP, right? Position of that, and that's how it is. This is the only thing moving, and if you want you can also take this position of this mass, right? You can take this position of this mass xm, but the displacement of pulley and this mass is going to be same. If you want you can keep it like that, otherwise no need, right? So displacement of this pulley and mass is same because this length of this string, there is a string here. Okay, this string length is not going to change, so I think it is better do not consider this. Unnecessary calculation will happen. Okay, so let us say you give a displacement here delta x. Delta x is the displacement to this. Same delta x you are giving here, right? So the force which is developed here, which is the tension here, or the force which is developed here, which you are writing tension is equal to k equivalent into delta x, right? Tension will be, right, equal to that. Okay, so here we need to compare this, right? So how do we compare it, right? So let us apply this concept here. So first of all there will be some elongation happening in this spring. Let's say delta L1 is the elongation happening in first spring. Here delta L2 is the elongation happening in the second spring. Okay, so total elongation delta L is equal to delta L1 plus delta L2, that will be there. Okay, and what is the total length of this spring? Total length of this spring is L, let us say, which is made up of x of the pulley plus again x of the P, right? Because it is going again back, and this side also this distance will, but I think this distance is fixed, isn't it? Let's say this distance is distance T. So xp plus T, right? Because this distance is not going to change. Pulley, upper pulley, and this is not going to change. So L becomes 2xp plus T, right? Now let's take delta here. Delta means change. So delta xp will be 2, delta xp. D is not going to change, so that will be 0. Okay, so now here delta L to experience displacement of xp, that means delta xp is same as delta x here. Note that displacement of the pull-in downward is same as delta x. Okay, so we are going to write this as delta x. Okay, now what is delta L? Change of length. From here we have written delta L1 plus delta L2. This is delta L1 plus delta L2 is 2 delta x. Okay, now elongation, you know, force is equal to k into x. So elongation is equal to force by k. So if you see elongation happening in the first string, that is force is there t by 2 by k1 we will take this. Okay, t by 2 by k1. Similarly, delta L2 is elongation is force by k. Force in the spring 2 is t by 2, that is tension. T by 2 same, right? T by 2 by k2. T by 2 by k2 is equal to 2 delta x. Now from here you can take t by 2 common, right? It will become 1 by k1 plus 1 by k2, isn't it? Is equal to 2 delta x. Now we want to bring in the same way t is equal to k equivalent into x form. So let's bring. So if you simplify, this t will become 2 will go that side, it will become 4, 2 will get multiplied, right? So and then this will become 1 by k1 plus 1 by k2 into delta x. Now you compare this factor is what is k equivalent. This factor is k equivalent. Now this thing which you are learning, you won't find in textbook this so crystal clear explanation. So t is equal to k equivalent x. So on comparing k equivalent delta x, you can say. So on comparing from comparison, you get k equivalent as 4 1 by k1 plus 1 by k2. Now this is what is you have to note. Some people think wrongly that, you know, k equivalent can be calculated simply by series and parallel. It's not possible. You may make mistake, you know, when you're trying to apply shortcuts, you will make mistake because you don't know what is going on. The problem of shortcut, you know, students learning just shortcut to solve problem, that seems very good, but inside you don't know anything what's happening, right? So it's a big risk. I won't just support this, you know, idea that you use simply shortcuts and make things easy. No, you need to learn these things. These are the consider how will you go for engineering without this engineering won't be tasty. If you enjoy engineering, then problem solving, you have to go deeper into the concept. Okay, so that's what it is. This is how k equivalent, and many places, if you search in Google and somewhere, they will just say that these two are in series. So k equivalent is given as 1 by k equivalent is 1 by k1 plus 1 by k2. No, that's wrong. Many places it is given wrong. Okay, this is the correct idea. Understood. So using these concepts, you can solve problems of, you know, string constraints, and lot of things can be done, right? I hope you have understood this, right? So with this, I think we have completed many things here. Then next session we will go for other topics in this chapter. Thank you for your attention.